Perfect. So this is one of our presentation-only papers. It's called PICCOLO, Point Cloud-Centric Omnidirectional Localization, and it will be presented by Junho Kim. Please, the stage is yours. And
yeah, so should I, is the screen being shared right now? Is the screen being shared right now? Okay, yeah, cool. Yeah, so let's get started. Hello, my name is Junho Kim from Seoul National University. Yeah, and before I start, I would personally like to thank the organizers of the workshop for giving me the chance to present our work in this workshop. Yeah, so today I will present our paper titled PICCOLO. It's short for Point Cloud-Centric Omnidirectional Localization. And yeah, so this is a work originally presented in ECCV 2021. Visual localization is definitely one of the main topics in today's workshop. And it's a very cheap localization method that finds the camera pose only using image input. And as we all know, pretty much the majority of visual localization literature focuses on perspective cameras. So as you can see on the right. But one of their limitations is that they have a relatively smaller field of view, which means that they can be vulnerable to scenes with repetitions, or there could be some possible scene changes, and those could all kind of make conventional localization to fail. So that's one of the main motivations for our research. So we decided to focus a little more on using omnidirectional cameras, which are more widely known, by the way, as panoramic views for localization, because they have a 360-degree field of view. So because they have a large field of view, they can be potentially more robust against those scene changes or some repetitive structure. Yeah, but they also have their catch, or their disadvantage, which is that they have a lot of severe distortion, as you can see here on the figure. So, so by directly applying some conventional localization might fail, and that's why we came up with our approach. Yeah, so our method, PICCOLO, is a simple and efficient algorithm for omnidirectional localization. And it basically takes two input modalities. The first one is the 360-degree image, the omnidirectional image you see on the left corner. And then it also takes a 3D point cloud. But here, one thing to note is that we're using a 3D colored point cloud, whereas usually in conventional localization, many people would try out with structure for motion maps, where you have 3D points associated with some visual features. But here, we are really just using raw 3D point cloud geometry and the color measurements for localization. Yeah, so that's one thing to note. And another thing about our method is that it's purely based on optimization, and I'm going to go over the details in the following slides. But because it's totally based on optimization, it could be usable in an off-the-shelf manner, as it doesn't involve any learning or training of neural networks. And so that's another desirable property of our algorithm. Yeah, so I'll directly move on to our main formulation. So PICCOLO, as I mentioned earlier, it's an optimization-based method. So it minimizes some loss function. And the loss function it minimizes is a novel loss called sampling loss. So what it does is, in a high level, it measures the difference between the point cloud color and the sampled location's color. And I'll just go over the details really quick. So for illustration, suppose you have a point cloud here. And I'm just going to show some pictorial descriptions of the 3 points. But yeah, so, and suppose you have some candidate camera pose shown in red. And what we do is we're going to project each of these 3D points to the 2D image space. And then since we have the query image, we can apply some differentiable sampling to look up the color value in that corresponding location in the image. And basically what sampling loss is doing, it is measuring the discrepancy between the original point cloud color against the sampled location's color. So to give a little more mathematical treatment of this concept, so sampling loss is basically a function of rotation and translation. So it's defined over 6TOF. And sorry, yeah. So I'll just briefly go over the equation here. So first of all, you have the point cloud coordinates x, and then you apply some rotation and translation on top of it. And so here, pi is the projection function. So this will map the 3D coordinates to the corresponding 2D image coordinates. And then we apply sampling on top of it. So I is the query image. And so once you apply sampling on top of it, you get the set of sampled color values from the image. And what sampling loss is doing is it's going to compare the sampled color values against the original point's color value and try to minimize that. So the optimization is still performed in the 60UF space, but we're imposing the loss in the color space. Yeah. So one nice thing about sampling loss is that it is point cloud centric, as you can see in our paper's title. And the reason why this is point cloud centric is because the loss is defined over each point in the point cloud. So it's not, so you can think about things like photometric loss, which kind of renders a synthetic view and compare that against the image. But here we're taking an alternative view where we would look at the point cloud color and compare that against the sampled color values. So that kind of helps us to be a little more free from the visual distortion that we would normally face if we were to use photometric loss and the variance for finding the pose. So that's one desirable property of our loss function. But then one downside is that it's highly non-convex depending on the scene. So say if you're going to do some omnidirectional localization in this room, then it will be totally fine because, well, the geometry is relatively simple. But if we were to do localization in some hallway, as you can see here, there's a lot of repetitive structure and there aren't a lot of visual features. So if you visualize the loss surface, so originally, as I mentioned earlier, it's 60UF, but here we are just doing a XY projection of the loss. But it can be really, really non-convex. So this is a very important challenge. And we'd rather have a naive solution for this. So given the point cloud, we would first divide this into some grid-like partitions. And so given each of these grid points, we look at the sampling loss values. And then we retrieve maybe like the top k smallest regions within that point cloud that has the smallest loss values. And then apply some continuous optimization on top of those selected points for further refinement. Yeah, so here is a visualization of what goes on after these promising starting points are selected. So usually this optimization is done in parallel for the selected starting points. So once you have these top k starting points selected, you can just apply some gradient descent optimization to minimize sampling loss. And yeah, so in practice, we just tried out with first order methods like Atom, but since our loss function is really, really simple to implement, we could also try out with some second order methods, which may actually result in better quality localization. Yeah, so here's a quick visualization of gradient descent. So let's see. Yeah. So what's happening here is I'm showing the optimization trajectory of one starting point. And so here's the query image. And here we have the point. Sorry, let's just see that again because it's kind of cool. So yeah, so it's making this optimization. And one thing that's very important to note here is that the starting point is fairly far away from the ground truth image. So if we were to try to do something similar with photometric loss, yeah, it's gonna not really end up getting into that global optimum, but because we are using some sampling loss, it gives us a much larger convergence basin, which kind of gives us a very efficient computation and also allows for more robust localization. Yeah, so I'll just briefly go over the experimental results. Yeah, so we did a lot of experiments in some various localization scenarios. So on the left corner, we tried out with some indoor scenes. We also tried some outdoor scenes. And then this is something very specific to our algorithm, but we also tried localizing in semantic labels. So I'm going to explain the details later. But because our algorithm is nearly 100% color-based, we can try this localization approach in like where we have a 3D map consisting of semantic labels and a query image consisting of semantic labels. And they can work because like our algorithm is essentially doing color matching. So we can do that. And then we also tried some more practical localization scenarios in like handheld scenes. So where you have a user like having a camera at hand and like moving around in indoor scenes. And then we also tried a robot mounted scenario in the middle. So we have a turtle bot. It's actually kind of occluded down there, but it's moving around some rooms. And we also tried that. And then for the last set of experiments, we also tried scene changes. So this is the case where like there's a large time gap between the 3D map building and the query image acquisition. So in this case, we originally scanned the wedding room, but then when we were taking the query images, like there were some construction going on, so it turned out to be a conference room. And so this is a very challenging scenario, but we just wanted to check if this could also work in our algorithm. Yeah, so these are just some qualitative results for indoor and outdoor localization. So here I'm showing the query image and the projected point cloud at the estimated camera pose. And you can see that our algorithm can work pretty well even in like these scenes containing a lot of repetitive structure. And here are some results in scenes with semantic labels. So this is actually some samples from the Stanford 2D 3DS dataset, where you have semantic labels available both for 2D and 3D. So what we're showing here is the 2D images, which are given as semantic labels, against the projections of the semantic maps. And on the right, I'm also showing the quantitative results. And you can see that compared to the baseline, we're getting fairly accurate localization. Yeah, and here are some additional qualitative samples for handheld and robot-mounted scenarios. And you can see that, especially for handheld cases, it's really challenging because a large amount of the field of view is being occluded by the hand. Like here you see some fingers. And this is like kind of inevitable in 360-degree vision because it's looking at the entire scene. So the user has to kind of cover some parts of the camera. But nevertheless, our algorithm can still kind of work really well in these things. Yeah, so now this is the last set of experiments. Yeah, so here we have scene changes. So basically, on the right, these are projections of the original 3D map when we did the 3D scan. And then here on the left, you have some query images. And you can see that even if there are very large amounts of scene changes, our algorithm can still kind of work quite robustly. And if you look at the quantitative samples on the right, so basically this table shows the localization accuracy in scenes containing scene changes and scenes that don't contain scene changes. And you can see that while there is a considerable amount of drop, our algorithm can still kind of, at least to a certain degree, perform robust localization. Yeah, so in conclusion, we propose PICCOLO, a simple, efficient algorithm for omnidirectional localization. And our algorithm minimizes sampling loss, which enforces each point to correctly sample from the query image. And as I've mentioned earlier, the formulation is point cloud centric, so it's kind of free from visual distortion that naturally occurs from panoramic views. And yeah, we expect PICCOLO to be extensively applied to virtual reality or robotics applications where omnidirectional cameras are present. Yeah, so thanks for listening, and if you have any questions, I'm happy to answer them. Are there any questions? Yes?
We wait for the microphone.
Thanks for presentation. I have a question about the speed. Can you reach the real time? How many? If I query an image, how many seconds it needs?
Yeah, actually, that's a very important question. So, yeah, well, currently, yeah, our system. So once you do optimization, it takes less than a second for optimizing a single starting point. But since we're doing it in parallel, we can optimize multiple starting points within a second. So that's good. But there are a few design choices that we can consider to make the algorithm even faster. Like for example, maybe we can like try to use a smaller number of iterations for gradient descent, or kind of do some downsampling in the point cloud to operate on more sparser set of points, because that would also make the algorithm much more faster. But yeah, for now, I mean, at least if you try this on an initial set of the default setup, it would take around a second, but it can get a lot faster. Are there any other questions?
Yes.
Yeah.
How can you adapt your method to large-scale scenarios? Or, for example, if the query image is pretty far from the current location. So how can you handle this situation?
So I'm not sure if I understood your question correctly, but are you talking about a scenario where like the starting point is really far away from the query image, right?
Right.
Yeah. So to cope with that, it's also important to well partition the original point cloud. So for example, if you're trying to localize, say, in a hallway, and you make two like extensively sparse partitions, then the gradient descent might not reach the goal point. So yeah, that's a very important design choice that we need to make. And in practice, what we do is, I think, so maybe say in this room, you would make about 20 by 20 by 20 grid partitions and test each of these sampling loss values and then just choose the top K and do optimization. Yeah. Are there any other questions?
Yeah, I have another question regarding the query. What happens if you would have perspective cameras for query time? Would it also kind of work, or can you adapt the algorithm to make it work?
Yeah, that's actually another really good question. We didn't report any official results in the paper, but I was also really curious if we could do that, and it does work to a certain degree. But one catch is that, so like if you recall the loss function, the reason why this can be point cloud centric is because the image projection is happening in a sphere, so it's looking at everything around it. But once it becomes a perspective image, like the loss function is like, I mean, like strictly speaking, it's not like completely continuous, because once you like kind of make some rotations or something like that, then the visibility of the points start to change. So it works to a certain degree, but there are some limitations if you're going to use it for perspective images. Yeah. Yep.
Okay.
So you mentioned like it will take less than 1 second, but on which device? On a CPU, GPU?
Oh, on a GPU, yeah. If you were going to do it on a CPU, you need to do a lot of downsampling of the point clouds to make it a little more affordable.
Okay, and what's the resolution of the point cloud?
I think maybe around like 10 million, maybe.
Okay.
But it could reach 100 million. Like so in practice, at least in our implementation, there seems to be this breakdown point. So like once you go over a certain number of points, it starts to get a little bit more slower. But before that, like the time is kind of similar. Yeah, and irrelevant to the number of points. So,
Okay,
yeah.
thanks.
Yeah, you're welcome. Thank you.